Group C from Biology Inspired Robotics. This module is all focused about building novel robotic techniques inspired by biology, so we decided to take inspiration from the humble tumbleweed. Tumbleweed rolls across planes, bouncing over objects. So we took this and built an exoskeleton and put some fans inside it to try and emulate this.
Yeah, I'm kind of skeptical that it'll work, but I'll go along with it. I just don't think we're going to like reinvent the wheel or something here.
On to something really big here. We're literally reinventing the wheel. Hi, phoning about the tumbleweed robot again? Hello? Hello? Can someone get an answer on the phone? They just hung up on me.
Now I'm going to hand over to Rob, who's going to read off a long list of tech specs for the robot.
We'll start off with the specs for the battery. It's got a 14.8 volt 4-cell LiPo battery with 180.
Yeah, so I built an old exoskeleton and it didn't really work. It wasn't really structurally sound. So then I went back home to Ireland holidays and built it there. I couldn't bring it across. EasyJet was really strict with their luggage and they got really nervous when I was trying to bring it back, like pipes and wires from Belfast, but I'll just build it here and it'll be fine.
What you're seeing on your screen now is a couple of examples of the exoskeletons that we initially constructed. They didn't make the final cut, although they were a very good jumping off point for our final design. Now we're going to check back in with Rob and see how he's getting on with that list of specifications.
The casing is made of PVC piping with a 2200mm circumference. The gimbal inside is 3 rings of 470mm.
Wow, would you look at that? He's still going. Right, in the next bit, it's a bit more serious. I'm going to talk to you about the health and safety of the project and everything we've had to do involving that.
So obviously the big health and safety risk with Frank is he's got fan blades spinning at like 39,000 RPM. If one of those comes off, you're going to know about it. But with everything spinning, if the box breaks, you can have debris, which we might have had.
Oh god!
We also had extra health and safety measures to deal with that. So we had a kill switch for if it started spinning up too fast.
There wasn't a kill switch. Matt, wait, was there meant to be a kill switch?
We can just cut it off. And we also had a net over the top to catch any debris in case it flew off. While we went inside the netting, you had to wear safety glasses and gloves the whole time.
I think this is a great success. There are so many positives we could like. Look, come. Look. So if you just.
So while I was having a little bit of a breakdown, I'm just going to tell you about the other stuff we've done outside of the exoskeleton. So our motor control system is 2 fans that power the robot and push it along. We've got a communications array that's able to bidirectionally communicate with the robot to send and receive control signals. We've also got a gimbal that keeps the motor stable while it moves along, so that the motors always give the same propulsion in the same direction.
It's a circle. Yeah, it wasn't a complete disaster, but it was quite close to it. It didn't do what we wanted it to do. It just kind of rolled around in a circle. We got there in the end, I guess. We have something to show for it, so that's a plus.
Wait, where's Rob? Is he still going?
We use 433 megahertz LoRa for communication between our controller, the ESP32, and our base.
So sadly now at the end I've got to cover the bits that didn't work and why that's the case. What you're seeing here now is Anand and I testing the communications in lab conditions. We were able to correctly verify the sending and receiving of packets to the motor. However, this later failed. We think that possibly one of the radios was damaged during a collision. This then left us with only one working radio, which meant we could no longer communicate with the robot. So all future testing had to be done by flashing the commands directly to the robot itself, and then providing a delay to allow operators to get in and out of the system safely. After the minor disaster of the first test, we added 2 kill switches, one of which you're about to see in action.
And once this hits 50, it's at 40, 45, 50, 51, and kill switch. And that's by comms, and it's working.
Nice.
Oh? It works!
80 minutes later.
Why doesn't this work?
On screen now was one of our final tests. This was where we verified that the ESC had probably most likely burnt out due to the different behaviours of the two fans. We easily verified by eye that one fan simply was not moving as fast as the other. Conversely, we got a very strong performance out of our other motor, and as you can see, the whole body actually started to rock. So we believe that given an opportunity where both motors worked, that it actually would have moved and rolled with relative ease. Overall, we believe the project was close to working, but we were just kneecapped by two defective components right at the end.